calculators and approximate numbers. This is going to be one of those foundational sections where we're going to be using this material sort of throughout the course. And really focusing on this idea of it being a technical mathematics course, we're going to be using our calculator a lot, but like any piece of technology, we need to know how to use it properly depending on the context. So let's get right into a sort of technical example. When we're measuring something, like say the current in a circuit or something like that, if you have a multimeter and you're trying to do that, we're limited in some way by the precision of our measuring devices. Our measuring devices only tell us a certain amount of information here. And the thing is that most numbers that we deal with in a technical or scientific instance are what we call approximate numbers, having been determined by some sort of measurement. Right, we use scales, right? We use, again, a multimeter, something like that. We have all these various tools that gather this data for us, but they only have a certain amount of specificity because, after all, they're technical devices. And when we run into these sorts of things, we have certain rules that we have to work with them. But not all numbers are like this. Some numbers are what we call exact numbers. And an exact number is something that's determined by some sort of definition or accounting process. After all, you've got like 1 child or 2 child or 3 children or 0 children, right? So you only can have one of those sorts of whole number results in those sorts of instances. So let's look at a couple of examples to separate these two notions here. When we say there's 3 feet in a yard, that is by definition. That is by definition how those two things relate. So that is an exact number. When we say that there are 3 feet in a yard, there are exactly 3 feet in a yard. Now, if we say Kevin is 1.87 meters tall, well, that's because we've used some sort of measuring device to make that assessment. So that is an approximate number. Let's say there's a hardware store and it has 92 pieces of drywall in stock. Well, the 92 there means they have exactly 92, right? They can't have 91 and a half pieces of drywall in stock. They either have it or they don't. So this would be an instance of an exact number. Now, let's say each piece of drywall measures 4 feet wide. Well, again, even though it's a whole number, it's still an approximate measurement. It might be slightly off in either direction and still called a 4-foot wide piece. So that is, again, an approximate measurement here. Suppose, again, at this hardware store, this drywall sells for $14.99. Well, that is the specified defined cost there, so that would be an exact number. It's not plus or minus something, right? It is exactly $14.99. When they say they charge you $14.99, that is what they charge you. One more example here, let's say the mass of a battery is 37 grams. Well, again, even if it might be to some sort of precision, which we'll talk about more here, all we have here is that it has been measured on some sort of scale or something like that, so this would be another instance of an approximate number. So note that exact versus approximate doesn't necessarily mean like decimal versus whole number. It's really just this question of, has this been measured with some sort of measuring device versus has it been sort of defined or counted to be this way, in which case it's an exact number. And let's delve into what exactly it means for something to be approximate, right? If we say that the mass of a battery is 37 grams, and the scale only gives us measurements to the nearest gram, then that scale is making a decision to round in one way or another. So the real mass of that thing could be somewhere between 36.5 and 37.5 grams, right? If it were slightly less than 37.5, it would show up as being 37 grams on our scale. So if that's as much information as we know for certain based on our measurement device, that is sort of the amount of confidence that we can have in that. We have a name for those digits. The digits that specify the particular value in an approximate number are called the significant digits. In other words, they're the sort of digits that we can say that we know with confidence. We know with confidence based on our scale that the mass of that battery is 37 grams. But I can't tell you like more information than that. So for instance, in that example, this would mean we would have 2 significant digits in that number. We're going to be talking a whole lot about numbers in this class, and one of the things we're going to have to keep in mind is place value, right? Whenever we're talking about a number relative to a decimal point, each of those different numbers has a particular place value, which indicates the size of the number there. So it's just a sort of review of the various tenths place, hundredths place, etc. You can review that table if you're a bit rusty on those sorts of things, but we're going to get into more practice with that as well. All right, so then what's the deal with significant digits? What makes something significant or not? Well, we're going to specify a few rules here for how this works, and then we'll see how this works in a particular example. The first thing we're going to note is that all non-zero digits are going to be significant. Again, imagine you put something on a scale and it shows up with some particular number. This is telling us which of those numbers are sort of meaningful pieces of information in essence. Now, zeros are going to be significant sometimes, but there have to be certain rules that apply for that. So if we have a 0 between other non-zero digits, those are going to be counted as significant. So in fact, I'm going to jump down to the first part of example 2 to illustrate this. So when we're counting the number of significant digits in the following numbers, again, imagine that our scale reads 70.34. Well, all of those digits are significant because every non-zero one is significant, and the 0 one, because it's in between 2 non-zero ones, tells us information. So all of those would be significant, so there would be 4 significant digits there. Now, in some circumstances, zeros will be significant, and in other ones they won't. So we'll specify that in the next 3 rules here. The first thing we're going to note is that leading zeros are not significant. So if they show up before any non-zero digits, this happens mostly with decimals, they're not informative really for us. So we are going to say that they are not significant. And then the other sort of place we can see zeros would be trailing zeros, zeros at the end. We're going to say that those are only significant if they are after a decimal point and after all non-zero numbers. So let's look at the next 2 examples to kind of illustrate this idea. When we see the number 80,300, we know that there's 80,000, we know that there's 300, but it's not telling us any information about the tens or the ones, right? So we might like estimate a stadium attendance or something like that as being 80,300. That suggests to me that I know how many people there are up to that 100 spot, but maybe down to the individual or maybe even to within 10 people, I don't quite know. So in this case, we start counting significance at the 8, and we count all the way until we reach our last non-zero digit, which is that 3. So that means I have 1, 2, 3 significant digits there. So that's what we do with those trailing zeros. We don't count them, basically. Now, what about if the zeros start us off? Well, again, those ones do not count. So when we see a number, again, imagine we measured something to be, say, 0.032 milliliters. We took like a tiny little pipette and measured that amount of liquid, for instance. Well, the 0.00, the 0.0, neither of those tell me any information. Again, imagine we have a very small measuring device. The significance only comes once we hit that non-zero digit. So that digit starts with the 3, ends when we run out of digits. So that would be 2 significant digits there. Now, one last thing that we will mention here, and that is when we run into something like 410 followed by a decimal point. So when we write a decimal point at the end of the number, that actually tells me to count that 0 as significant. So this is our last rule here. All 0 digits before a decimal point will be counted as significant. So when I'm putting that decimal spot, it's basically a convention, a notation to say that I know that this thing is exactly 410, right? So it's not confusing and saying, well, maybe it's around 410. It's saying, no, it's exactly 410 to within that ones place, right? It might be slightly less, like a half less, but it's not like 3 or 4 off. So again, when we're looking at the significant digits, I'm going to generally do this as you've kind of gotten by underlining the digits. That's going to be important for doing operations with these in a little bit. So we say that there's 3 significant digits there. One last example, so we have 5.0. Well, again, coming back to this rule here, trailing zeros are only significant if they're after a decimal point. So, since it's after a decimal point, this is again telling me 5.0, so I have confidence what that tenths place, that spot immediately after the decimal spot is, so that 0 is significant. So again, in this case, we have 2 significant digits. So again, you can really think about these rules as telling you where do I start counting significance and where do I stop. See, example C here gives us an idea that we only start counting significance once we reach our first non-zero number, and then we stop basically when we run out of digits, when we run out of non-zero digits. So like for instance, on the 80,300, we stopped at the 3. With the one exception being there, if we put a decimal point at the end, that tells me I have more specificity. So we have another name for this when we talk about how many significant digits we have. We call that the accuracy. So the accuracy of a number is exactly how many significant digits it has. We have another term, which sounds similar, but in our course, they're going to mean very specific things, so we want to make sure we separate those two ideas. And that's the other thing of precision. So the precision of a number is going to be the decimal position of the last significant digit. Again, you can think about like the precision of some sort of measuring device. So you might have a bathroom scale that's digital that shows it to the nearest pound, or maybe to the nearest tenth of a pound, right? So that's telling you that precision is saying how much, how far can you go, how granular can you get within that measuring device. So let's revisit the same numbers and talk about precision there. So again, we're going to find the last significant digit, which we've already done above, and then say what place that is. So the last one here is that 4. Well, again, from that sheet on the previous page here, this represents hundreds. Right? So this would be 1/100, the fraction 1 over 100 of one whole quantity there. Here, that number represents, again, this 80,300, so that is actually the hundreds place. Here, when we have it as the third decimal spot after, this would be the thousandths. Again, we noted in this one that we do have specificity to that ones place. So we know to the nearest whole number how much that is. And then finally 5.0, well, again, the last significant digit we have there is the 0. So this would be to the tenths place. So again, to recap, accuracy means how many significant digits it has, and precision tells me how far out I can go. What's the last significant digit that we have? All right, so now we're going to do some math with these couple of ideas here. We're going to talk about rounding. This is probably a thing you've seen before, right? When we're trying to figure out how to round something, we have some specified digit that we want to round, and we look to the right of that, right? The place value is smaller than that. And if that digit is less than 5, 0, 1, 2, 3, or 4, we're going to go ahead and keep the rounding digit the same and basically drop off the rest of them. So everything afterward, we're just going to make them 0. We're not going to even write them down. Whereas if we pick, if we see that the digit to the right is bigger than 4, if it's 5 or greater, we're going to add 1 to the rounding digit. And then again, we're going to make all the digits afterward be equal to 0, and this is what we call rounding up. So let's say we want to round 70.34 to 3 significant digits. Well, we already mentioned before that it has 4 significant digits, but if we just focus on those first 3, really when we're saying rounding, we're imagining that, again, imagine you had something that had a mass of 70.34 grams, and you put it on a scale that only gave you accuracy to the nearest tenth. So there's the question of which would this go to? Would it go down to the smaller number of 70.3, or would it go up to the number of 70.4? Well, 70.34 is closer to 70.3, so when we round it to 3 significant digits, it's going to round down. Again, the rounding digit here would be 3, the one to the right of that is 4. Since it's less than 5, we round down. Let's say we have 1,089.5. We want to round it to 4 significant digits. Again, we can see that we start off with 5 because all of those digits are significant. So the 4 would mean I have to round the 9 either up or down. Well, because the next digit is 5, sort of by convention, we choose to round up 5. There's different conventions out there, but that is how we choose to do it. And if we're going to round this thing up, well, again, think about what 2 numbers the 89 is closest to, right? We know 89.5 is between 89 and 90. So here, since we're rounding up, we're going to round that 89 up to the next number, which will be 90. So this will be 1,090, but this is where that notation bit comes in again. We want to indicate here that all of these digits are significant. The way that this number is written down right now, that last 0 is trailing 0. It doesn't sort of indicate that I know this thing to that ones place. So the way that we're going to indicate clearly that we do know to the ones place is to, again, go ahead and put that decimal at the very end here. Lastly, let's say we want to round 8.649 to 2 significant digits. Well, again, that means we want to look, those first 2 significant digits, we always start counting significance at the left side of the number, at the big part of the number. And we want to know, again, which number is this thing closest to the nearest tenth. It's either closer to 8.6 or it's closer to 8.7. Well, again, we're going to look to the digit immediately to the right, which is the 4. Since 4 is less than 5, that means we're going to be rounding down here. So we're going to lop off everything from the 4 past and just stick with the 8.6. And I bring up this particular example just to note that rounding doesn't have this sort of cascade effect. We don't say that the 9 causes the 4 to round up to a 5, and then that makes this thing round up. That's not what's happening. Again, we're really saying, which number is this closer to, 8.6 or 8.7? Well, 49 is closer to 0 than it is to 100, so that whole chunk is going to get lopped off, and that thing will get rounded to 8.6. Again, rounding is going to be one of those things we have to do sort of throughout the course, so it's something we definitely want to get good at. Now let's talk about doing approximation, doing operations with these approximate numbers. So when I say operations, I mean addition, subtraction, etc. So there's some rules for this that we're going to do on the next page, but before we do that, let's just introduce the principle of it. Suppose we have a child that weighs 61.7 pounds, putting on a backpack that weighs 7.82 pounds. We want to know what is the combined weight, and also, what does it make sense to round to? Well, to do a combined weight, clearly we're going to be taking one weight and then adding another weight. So we're going to be doing that 61.7 pounds plus the 7.82 pounds. So now if we go ahead and use our little calculator, by the way, I'm going to be using a TI-30X for most of these. You definitely need a calculator for this course. If you have one of these little fancy graphing calculators, that's great. It does wonderful things, but you will definitely want at least some sort of scientific calculator. You can usually find them for about $10 or something like that. So feel free to get whatever one you want, whichever one if you have comfort using a particular one, that's great. But you definitely don't want to be doing this stuff on your phones because those are terrible calculators. Anyhow, coming back to this problem, we add up those two numbers and we get 69.52. So I'm gonna go ahead and write down what my calculator tells me here, and then we're gonna have to figure out how we want to actually report this result. Well, we can ask ourselves the question, how confident are we in that number, right? Well, we know that the child weighs 61.7 pounds, but there's some amount of imprecision with that one, right? So we might be off a little bit, right? If our scale only goes to the nearest tenth, I'm not any more confident than the nearest tenth. So when I add that 7.82, my answer is only as precise as my least precise measuring instrument here. So let me write that down here. My measurement is only as precise as the least precise instrument. Right, again, imagine you have like a little kitchen scale that measures to like 1/10 of a gram or something like that, and then you have your bathroom scale, which might measure to the nearest 1/10 of a pound or something like that. When you combine those two, you are limited by the precision of that bathroom scale, even if your kitchen scale is super precise. So when we report this result, we are going to report to the least precise, which would be here, that 1/10 here. In other words, we're going to need to round to the nearest 10th. So we got 69.52. Again, we look to the digit to the right of the 10th place, that's a 2, so we round it down. So we are going to say that these two combined weights are going to be 69.5 pounds. So that's how it works for adding numbers. Let's explore another scenario. What if we're multiplying numbers together? We're going to be doing a bunch of geometry in this course in chapter 2, so we'll be introducing some formulas a little bit later on. But before we get into the formulas, let's just talk about a particular example here. Let's say we have a rectangular plot of land that's measured to be 174.8 feet by 81.3 feet. And the way we find the area for a rectangle is to multiply length and width, as we'll talk about in chapter 2. So let's figure out about what the area of this plot is in square feet. And what we're going to do is we're going to find an answer that is as accurate as possible. And again, when we say as accurate as possible, we really want to say as accurate as is indicated by my instruments of measurement. So let's be systematic about this. Let's imagine here that we, again, it's always nice to draw a little picture here. Let's imagine we actually had a rectangular plot. It's not necessarily the scale here, but I've got 81.3 feet as the short side and then 174.8 feet as the long side. Again, both of these numbers we've indicated here that my measuring device is only accurate to the nearest 1/10 of a foot. So let's build in that error allowance into my calculation. Let's come up with a low estimate and an upper estimate for this. Again, there will be a procedure for this, so you don't have to take this approach, but this will just tell us why we take the approach that we do. So let's imagine that both of these numbers here were actually slightly larger than the actual area, right? The actual amount of feet on each side. Well, that would mean that this 174.8 feet was actually slightly larger than the real number. We talked about how, from rounding, that this thing could have been rounded up, right? In fact, the smallest number it could have been rounded up from would be 174.75, excuse me. And this number as well could be as low as 81.25. Well, if we find the area by multiplying length times width, well, let's go ahead and, got my fancy calculator, we'll do the same thing. 174.75, and then we're going to do times 81.25. I'm going to report all the decimals for right now, and then we're going to talk about how to interpret this in a second. But this number comes out to be, what is this, 14198, so that's 14,198.4375. Again, we will not be reporting all of those numbers, but that is just what my calculator said. Well, let's likewise figure out, suppose that our error was in the other direction. Say that this was actually a little bit bigger than the number that we reported here, right? It could be up to 174.85 feet, right? Technically at 8.5 we would have rounded up, but if it were like 8.4999 or something like that, it still would have rounded down, like we saw. So again, we're just going to say a worst case scenario. Suppose that we were off by that 1/5 of a foot, or sorry, 5/100 of a foot in the other direction. Well, if I look at those two numbers rounded up here, oh yeah, and I forgot to mention this. This is in square feet. When we multiply feet by feet, we get square feet. We'll explore that again later in this chapter. If I take these numbers again, multiply them to 174.85 times 81.35, I get 14,224. I put the comma after those three digits there, and then 0.0475, and that's in square feet. So again, let's come back to that question of what was it that we wanted to answer? We wanted to report a value that was as accurate as possible. So knowing that there is some amount of error in this approximate number, the question is, looking at my lower estimate and my upper estimate, how many digits am I justified in reporting? Well, it's somewhere between 14,198, etc., and 14,224. Well, we definitely know it's 14,000. And then if we look to the next decimal, or the next place value, the hundredths place, note that if we were to round both of those things, they would both get rounded to the value of 2. This one would get rounded up, this one would get rounded down, but we would have agreement on those up through that hundredths place. So the actual value, so I'll call it our reasonable estimate, how many digits can we actually report with confidence? That would be to the hundredths place. So that would be 14,200. Again, to say more than this would be to sort of give a false indication of how much information we have here. We never want to over-report our findings here because that could be misleading here. So what's the significance of this? Well, if we got 14,200, well, that's going to give us a suggestion for what we do in this case number 2. So let's synthesize what we just did. On the previous page, we said that the precision was limited by the precision of the least precise instrument. So when we add or subtract approximate numbers, that means our precision is going to be expressed by the least precise number. Compare that to what we have here with a rectangular plot of land when we did multiplication. We note that my answer here, when we ask how many significant digits does this have, well, again, remember the trailing zeros don't count because I don't have a decimal place there. So all I had was 3. The other thing we can note is that 3 is the number of significant digits. 1.3. So our guideline here is that when we have approximate numbers that are multiplied or divided, the result is going to be expressed with the accuracy, which is to say number of significant digits, of the least accurate number. One of the things we're going to be talking about more in later sections in this class, but we might as well introduce this idea now. When we take the root of something or the power of something, we use an exponent, and we have that for some approximate number, we're going to express that with the accuracy of the number. So the same number of significant digits. So let's go ahead and use these guidelines to perform a few calculations here. Now, the other thing that I didn't mention in these above is that we are going to do the calculations first, and then we're going to round. So you don't want to round too early, because again, after all, if you had like 0.25 and then another 0.25 and another 0.25, and you add those things up, well, that extra little 5 there ends up contributing and adding stuff there. So we're going to do our calculations first and then round at the end. So here I've got some addition and subtraction going on. So again, let's first note how many significant digits we have in each of these. Or actually, before I do that, let me make sure I note which of these rules is going to be applied. So here, we're looking to answer both of those questions. So the first question that we asked was, what's the deal with the significant digits? Well, this one has 3, this one has 2, and this one has 3, right? The first 0 doesn't count. But since I'm adding and subtracting these ones, again, imagine that you had different scales that gave you, one gave you to within the nearest hundredth, one gave you to within the nearest tenth, one gave you to within the nearest thousandth. Well, you are limited by the one that is to the nearest tenth. So what we're going to do here is start by adding up those numbers, 4.82 plus 8.1 plus 0.98, oops, sorry, excuse me, minus 0.987, there we go. And we'll get 11.933. But that 11.933, again, our least precise is to the nearest tenth. So that means I am going to report this value to the nearest tenth. So I'm going to say that the sum and difference of these things here is going to be 11.9. Again, that is what I can be confident saying that this value is. This next one, we've got 47 times 608.2. Again, we're assuming these numbers are approximate so that these principles apply here. So again, first thing I'll do is I can multiply these numbers in my calculator. But again, I only want to report accuracy that is justified by the information that I have. With 47, again, all non-zero digits are significant. So this thing has 2 significant digits. And this one, remember, we start counting with a non-zero, and we stop counting with a non-zero if that's where it stops. So all of those are significant. So that is going to be 4 significant digits. Which is to say we have one number that's pretty accurate and one number that's not really that accurate. So if we don't know that this thing is exact, right, if it were like 47-ish, then we are limited by that accuracy of that number here. That tells me that my result that I'm going to report is going to be the accuracy of the least accurate number, so there's going to be 2 significant digits. Well, I computed that result right here, so since we know it's going to be the 2 significant digits, that number, and again, I can write down this number as a sort of intermediate step. This is not the actual result I'm reporting, because I do not have this level of confidence. The one that I have here is I only have confidence to that first 2 significant digits. So what does that mean? The value we're actually going to report here will be to the nearest thousandth. So we're going to have to round at that 8. So we're going to look to the right of it. Well, we see a 5 afterwards. So that means we're going to have to round this thing up and call this thing about 29,000. Again, the rules for multiplication and division work the same way. So if I have 0.68 divided by 302, again, this is what my calculator will tell me, but I only want to report as many values as I have confidence in. Well, this one, again, we have to build those skills we just built on a couple of pages ago. This number here, the 0.68, only has 2 significant digits because we don't start counting until we get that first non-zero digit. So this thing has 2 significant digits. The 302, again, all of those digits are significant, so that is 3 significant digits. Again, we're going to report with the accuracy of the least accurate number here. So again, when I am reporting my result, it is going to have to be with 2 significant digits. So when I write down this computation here, 2 significant digits, well, that means we have to interpret where we go with this thing, right? Remember, any of the zeros that we have in the front are not significant. So that one's not, that one's not, that one's not. We only start counting significance once we reach a non-zero digit here. So when we see that 0.0022516556, again, that's not the actual value that I'm going to be saying. The real value that I'm going to report here will be the 2 significant digits. Well, if I start counting here, I will stop counting here, and I will need to round that digit. Well, if we look to the digit to the right of it, it's a 5, so that tells me I need to round up. So that means this number is going to be expressed as 0.0023. Again, these are the values that we're actually reporting. That is as much confidence as we can have in those numbers. All right, we've got just a little bit left in this section. And let's get into some applications here, right? And we're talking about these instruments of measurement. Let's suppose we have, here's a principle. We're going to revisit this principle a little bit later. But when you have a voltage in a circuit, it can be found by multiplying the current by the resistance. And this is given that you have these things in volts, amperes, known as amps, and ohms for the measurement of resistance. So let's say your current measures 0.72 amperes and the resistance measures 330 ohms. We want to find the voltage. Again, if we just read that thing carefully again, it says multiply the current by the resistance. Okay, so that's my goal here. I want to find current times resistance. So that's going to be 0.72, and this is in amperes, times 330. By the way, another way that we sometimes represent multiplication is using parentheses, and ohms can be abbreviated with this symbol omega. Kind of clever bit of notation there. So we're multiplying the 0.72 amperes by the 330 ohms, and again, at this point, we want to figure out how confident I can be in reporting this resulting value. So let's count up the number of significant digits in both cases. So first, it's multiplication, so we're going to be reporting with the accuracy of the least accurate number. Well, in this case here, remember the first 0 doesn't count. We only start counting significance at non-zero digits. So this thing is going to have 2 of those significant digits. And then we have our 330 ohm resistance here. Well, again, that last 0 is subject to some amount of error, right? Manufacturing processes ultimately result in some amount of error, generally speaking. So here, we've only got 2 significant digits. Well, that means actually both of them are as accurate as one another. So our result is going to have 2 significant digits for the result. So now that I know what it is that I'm doing, I can figure out how to go ahead and report this result. We'll have 0.72 times 330. oops, let me switch back to black here. So the result here I get says 237.6, but what we just said is that, I'm going to write down that number here as a sort of intermediate step. In the future, we won't need to express this intermediate step here, but it's helpful just to illustrate. We only have confidence to within those first two significant digits, right? Which means I need to report this thing. I can report the hundreds place and the tens place, and that's it. So this number here, the way that we're actually going to report it is going to be 240, and this is given in volts, which is a pretty standard voltage in certain outlets. So the answer we can say here with confidence is 240 volts. We kind of mentioned this a little bit, but this is where we're going to have to really get more into our calculator. When we have multiple operations, we want to keep all of the digits in the intermediate step. So that is to say, we don't want to round. We're going to let all the numbers basically live in our calculator, and then round when we get to the end. So here we've got this example. We're going to perform the indicated operations, assuming all of these numbers are approximate, 4.265, et cetera, et cetera, et cetera. I will read that out to you. But I've got a product here, and then I've got it divided by a sum. Well, remember, we have two different rules for multiplication and for addition. So let's do each of these things kind of separate and then bring them together. So for these two things first, we want to figure out how we combine them. Well, since we're doing multiplication, we're going to be reporting with the accuracy of the least accurate number, which means count up the number of significant digits. Oh, this one, that's a pretty easy one. Definitely has 4 significant digits. The 2.60, we have to remember that if we have zeros after the decimal place and after numbers, they are significant. That is telling me I do know to the hundredth place that it is 60. It's not 59, it's not 61, it is 60. So those 3 digits are all significant, so that will mean we will have 3 significant digits. And now we're going to be dividing this thing by that sum. Well, before we do that, let's just look at what we get from that. We get 4.265 times 2.60, which honestly, you just write 2.6, it'll get you the same thing. So that first number tells me it's 11.089. So the way that the book does this, that I think is kind of a nice way to do it when we're doing these intermediate steps here, just kind of show some of our work, is I'm going to write down all the numbers that my calculator gives me, but then I'm going to indicate with my pen which of the digits are actually significant, right? So we could note here from the rule we discussed before, the product is as accurate as the least accurate number. So the product is going to be expressed with 3 significant digits. So that means that the first 3 significant digits that I have, or sorry, the first 3 digits are significant. So those are the ones that are significant, and we'll have to carry that through for the next step here. Now next we have this 3.7 plus the 5.14. Well, since we're adding, we are going to use the precision of the least precise. So when we're looking at the precision here, this is precise to the tenths. This one's precise to the hundredths. Well, we're going to use the precision of the least precise instrument. So we're going to divide by, let's add that up, 3.7 plus 5.14. 8.84. Again, we're going to make liberal use of our calculators here. If you can add that in your head, or if you want to add it on paper, you're welcome to. But the important thing here is it's that 8.84, but it's only precise to the tenths when we're reporting this. So we only have precision to that 8.8 number here. Well, now we have one last step here. There's a lot of steps to this problem. It's actually kind of complicated. We have to keep track of these digits at each of these intermediate steps and keep track of these numbers. And now we want to go ahead and combine these numbers, noting that this one has 3 significant digits. That's what we observed before. And this one, we only have precision to that tenths place. So that means the only ones of these digits that are significant are those first 2 of them. Aha, well now we remember that division, like multiplication, has the accuracy of the least accurate number. Well, the least accurate number is going to be that 8.84, which is really closer to 8.8. That's how we would report it. So again, from my rule here, my value, my result, is going to have 2 significant digits. Okay, so we're going to go ahead and use my 11.089, divide by my 8.84. And what do we get? We get 1.2544, etc. But we're only reporting this thing to 2 significant digits. So when I see this 1.2544, etc., I'm not going to write all these things because the precision there is meaningless, right? The actual value we are going to report here is going to be with 2 significant digits. So again, that's going to be 1 point something. So we have to round to that value here. That tenths place, well, since the digit after it is 5, means this is going to get rounded up. So we are going to report this result as being 1.3. Now, there's one last thing that we want to keep in mind for this section, which is that sometimes when we're working with approximate numbers, we also have some other numbers that are exact. And sometimes we're going to combine those exact numbers with the approximate numbers, right? So like we have the drywall sheets that are each 4 feet wide, but we know that we have exactly 92 of them. Well, knowing that we have exactly 92 of them means that that number is not limiting my accuracy or precision in any way. So the accuracy and precision is only going to be limited by whatever numbers are approximate. So like we mentioned, some unit conversions, which we'll talk about in another section, are precise. Excuse me, I used the wrong word. Are exact. So for instance, there's exactly 3 feet in a yard. There's also exactly 5,280 feet in a mile. Sort of a mile by definition is 5,280 feet. So let's say we measure something to be approximately 1.6 miles. So again, that's saying to within the nearest tenth. And we want to know how many feet are there. Well, we've got 5,280 times the 1.6. Well, the fact that this is an exact number means we don't even need to think about how many significant digits it has. We know it's exactly 5,280. There is no rounding, there's no measurement involved whatsoever. So we are only going to look at the accuracy here of that second number. Well, we see it has 2 significant digits. So we are going to use 2 significant digits in our answer. Again, we're not even going to think about how many are in that one. We are going to use the 1.6, the 2 significant digits in that number, and use that to report our result. Again, 5,280 times 1.6 gets me 8,448. But my result here is only going to have 2 significant digits, which means that when I have this 8,448, I'm going to have to round it at the hundredths place, right? That's the second significant digit. The digit to the right is a 4, it's less than 5, so that means we are going to round down this number here, and that will be 8,400. And of course, note, we've got a meaningful application here, right? So our answer here would be expressed in feet. I kind of skipped over some of the unit stuff for right now in terms of thinking about unit conversion, because that is something we're going to explore in the next section. So I will see you then, wherever that may be.